Welcome to a new session on the massive open online course Introductory Concepts of Digital Computing offered by Swayam. In the last lecture, we discussed about the synchronous up and synchronous down counters. You can combine the functionalities of up counter and down counter in one circuit, and it is called as binary up down counter. Another name for this circuit is bidirectional counter. Such a counter can either count up or down. Hope you remember about the bidirectional shift register we discussed while learning registers. It was capable of either shifting left or right, and there was a control signal to decide the mode of operation. The same concept is applied here too. The control signal up down controls the direction of counting. Look into the diagram of the 4-bit bidirectional counter shown here. It has 3 inputs: the clock signal, the input which is maintained as 1 always, and the control signal up down. There are 4 outputs for this counter, Q0 to Q3. There are 4 flip-flops and some logic gates to control its working. Note the point that it is a synchronous counter, hence the same clock pulse is provided to all the flip-flops. You can see that this counter is made of 4 T flip-flops, but it is possible to use JK flip-flops, tying together the inputs and keeping it to the level high. Also note that there are AND gates at 2 levels, one receiving the output Q signifying the up counter, and the other one receiving the complement of the output Q dash signifying the down counter. Now things are pretty simple and straightforward. According to the figure, if the control signal is at the low level or at 0, then the AND gates connected to the complement of the output will be enabled. This is because a NOT gate is attached to complement the control signal. Since the complement of the output is considered, it will start counting in the reverse direction from the value that is stored in the flip-flop. When the control signal is up, then the AND gates at the higher level gets enabled and the counting progresses in the forward direction from where it has stopped. There is an OR gate too, connecting the outputs of the AND gates. Now let us try out a scenario. Suppose the counter's current value is 0, 1, 0, 0 and the up-down control signal is 0. The lower AND gates gets that control signal as 1 now. The first flip-flop toggles its value for sure, no matter whatever be the value of its up-down signal. The Q0 becomes 1 now. Moving to the second flip-flop, its input is the result of the OR gate which has its inputs from 2 different AND gates. The topmost AND gate has inputs Q and the control signal which are 0 and 1 respectively. That AND gate has 0 as its output then. The AND gate connected below has 2 inputs again which are the complement of the previous value of the first flip-flop and the control signal. The output of this AND gate is 1. At this juncture, the second flip-flop has 1 as its input, enabling the toggling of the T flip-flop. The Q1 will be 1 then. Now consider the case of the third flip-flop. The output of the top AND gate is 0 because the control signal is 0, and the AND gate at the bottom takes the input from the complement of second flip-flop and the control signal and produces 1 as its output. This will toggle the third flip-flop too, turning Q2 as 0. In the case of the fourth flip-flop, the previous flip-flop's complement is 0 which produces a 0 at the output of the AND gate at the bottom. Topmost AND gate also produces 0. The OR gate has 2 zeros then, and this state will not toggle the flip-flop and will remain in its previous value, and Q3 will be 0 itself. So after this clock pulse, the value of the counter will be 0011, which is equivalent to decimal number 3. and the counter has decremented 1 from its previous value 4. Now, assume the control signal is 1 enabling the up signal. The value of the counter is 0, 0, 1, 1. The AND gates at the upper level gets enabled now. The first flip-flop will toggle anyhow, producing 0 at its terminal. The second flip-flop will receive the previous value of second low order bit, which is 1, and the up signal, which is also 1, turning the AND gate's output as 1. However, the AND gate at the bottom will have a 0 here because the control signal is negated. We can ignore the bottom AND gate for this cycle of clock pulse since it will always produce 0. The flip-flop will have 1 as the input and it complements the value. Thus, the Q1 becomes 0. The top AND gate to the third flip-flop produces 1 because the flip-flop's previous value from the last two flip-flops were 1. The output Q2 then becomes 1. The last flip-flop will remain in the same state because its input from the OR gate is 0. Why? Because the third bit of the previous value of the counter is 0, thus disabling the top AND gate. The bottom AND gate is already 0. So, Q3 has the value 0 itself. Now, the counter have the state as 0, 1, 0, 0 after incrementing it. Hope you understood the working of binary up-down counter. Next, in synchronous counters, we have in the pipeline is the BCD counter. It is used to count from 0 to 9 and resets itself back to 0. This works similar to the asynchronous BCD ripple counter, but with a difference. Here, the clock pulse applied to the flip-flops are the same. The BCD counter has to return back to 0 once it reaches the count 9. The logic diagram of the BCD synchronous counter is given here. It has 4 JK flip-flops and its inputs are maintained at high level. There are 4 outputs Q1, Q2, Q3 and Q4. Q1 is from the flip-flop FF1, Q2 from the flip-flop FF2, Q3 from the flip-flop FF3 and Q4 from FF4. How does it work? You know that since the BCD counter has to return to 0 when it reaches 9, the design of the circuit is not that straightforward. Some logic has to apply to toggle it and to reset the flip-flops. There are 4 conditions to ensure the toggling in proper manner. They are: the first condition, Q1 is toggled on every edge of the clock pulse. The second condition, Q2 is toggled when Q1 equal to 1 and Q3 is 1. The third condition, Q3 is toggled when Q1 and Q2 are 1. And the fourth condition, Q4 is toggled when Q1, Q2 and Q3 are 1. These are the conditions for toggling. Now, you need to define the logic to reset the counter. For that, you need to follow 2 more conditions. The first one, Q2 gets cleared when Q4 is 1 and Q1 is 0. Second one, Q4 gets cleared when Q3 and Q2 are 0 and Q1 is 1. Let us simulate the working of BCD counter now. Initially, the value is 0, 0, 0, 0. At the arrival of the first clock pulse, the LSB turns to 1. Here the first condition is met, no other conditions are applicable here. So, the output is 0, 0, 0, 1. In the next clock pulse, the LSB is toggled, and since the previous value of LSB was 1, Q2 also gets toggled because it satisfies the second condition of toggling. Now, the output of the counter is 0, 0, 1, 0. In the next clock pulse, the value turns to 0, 0, 1, 1 because only the first condition is satisfied. The next clock pulse is crucial because as per the conditions, the outputs Q1, Q2 and Q3 needs to be complemented. The counting of BCD operations is clearly summarized in the table. Look into the table for the toggling conditions from 1 to 4. If they are valid and satisfied, a tick mark is given, else it is mentioned as not applicable. The clearing conditions are also given here. You can easily make out that clearing happens only when the BCD counter reaches the highest value. Let us see what happens when the register is at the value 1001 and the next clock pulse arrives. The LSB is toggled, turning the 1 to 0. Since Q4 is 1, then you need to set Q2 as 0. And finally, the Q4 is set to 0. Because the Q3 and Q2 are 0, also the Q1 is 1. And the state of the counter becomes 0000. That is how the BCD counter works and resets to 0 when it reaches the value 1001. The synchronous counters can be cascaded to form a counter for decimal numbers of any length. If you want to count from 0 to 99, then we need to have 2 BCD counters connected in cascade. From 0 to 999, we need to have 3 BCD counters connected in cascade. Now, let me stop discussions on BCD counter and move to the next. The next synchronous counter we are going to deal with is the ring counter. A ring counter is a shift register which shifts its bits in a circular manner. Moreover, the output of the last flip-flop will be fed as input to the first flip-flop. This is almost like a serial in serial out register, but the difference is that the value will be circulated in a closed loop. In this counter, only one flip-flop will be set at a particular time. All the other flip-flops will be cleared. This single bit will be shifted to the next flip-flop at the application of the next clock pulse. And for each clock pulse, this is repeated and finally, the bit returns to its earlier position. That is why it is known as the ring counter. Look at the logic diagram. The same clock pulse is applied to each flip-flop, hence it is synchronous. The flip-flops are really chained in the sense that each flip-flop receives input from the previous flip-flop and there is one more input, reset. What is it meant for? It is for clearing the values inside all the flip-flops. It is necessary because as per the nature of ring counter, a value once entered will be in an infinite loop. So, to reset the value of the counter to 0, we use the reset signal. Now, how does it work? Suppose the initial value of the counter is 1000. Let us name the 4 flip-flops as F1 to F4 starting from the LSB to the MSB. On the arrival of the first clock pulse, F1 shifts its value to F2, F2 will shift to F3, F3 will shift to F4 and finally F4 to F1. If you follow this order, 1000 becomes 0100. Now, for the second clock pulse, the content will be 0010. In the next clock pulse, it will be 0001 and finally returns to 1000 in the next clock pulse. You might have observed that the register returned to the original value in the 4th clock pulse. Why on 4th clock pulse? Because it is a 4-bit register. So, in general, an n-bit ring counter circuit returns to its initial value once in every n clock pulse, and every single flip-flop will be in one state once in every n clock pulse. The values of all the 4 flip-flops is summarized in the table given here. The initial value and the time when they return is highlighted in yellow. Let us continue our session with a special counter known as Johnson's counter. The Johnson's counter is a special type of ring counter where it exactly follows the procedure of the ring counter. The difference is in the feedback path where the complement of the output is connected back to the first flip-flop. See the table. Initially, the register had the value 0001. On the arrival of the first clock pulse, QA shift the value to QB, QB to QC and QC to QD, and please note that the complement of the QD is shifted back to QA. What will be the output then? 1100. One more 1 is present in the counter because it got replicated from its previous flip-flop. What happens in the next clock pulse then? This shifting happens in the above order resulting in 1110. One more 1 is replicated. You can guess what happens in the next cycle. One more 1 gets replicated and becomes 1111. Now there is a twist. The clock pulse arrives again. This time QD will feed 0 into QA because the complement of the last flip-flop is connected back to the first flip-flop. You will get the register's value as 0111. In the next clock pulse 0 gets replicated again and the state becomes 0011. On the arrival of the successive clock pulses, the register will have the values 0001 and 0000. If you have the next clock pulse to trigger the circuit, then the register returns back to the initial value 1000. You might have observed here that the register returned to the original value in the 8th clock pulse, not in the 4th clock pulse as in the case of the ring counter. Then we can generalize as in an n-bit Johnson's counter, the circuit returns to its initial value once in every 2n clock pulse. The values of all the 4 flip-flops during the shifting operations is summarized in the table given here. Since there is a twist happening in the Johnson's counter after every n clock pulses, we call it as twisted ring counters. It is also known as switch tail ring counters because the switching happens at the tail of the ring counter. So, to conclude, the twisted ring counter is a circular shift register with the complement output of the last flip-flop connected to the input of the first flip-flop. Then next we are going to discuss mod n counter. Let us move to the last type of the counter, mod n counter. So far, when we discussed about the counters, we set their initial value as 0000 or 1111. Now, suppose you want to start counting with a user defined value. How will we do that? We have to load that value to the counter, which requires a parallel load capability in the counter. We can modify the counters to add one more control signal, which when equals to 1 disable the count sequence and starts the parallel loading. If the control signal is 0, it will work as a counter. Counters with this extra functionality of parallel loading is very useful in the design of the digital systems. Such circuits can be used to generate any desired number of count sequences. If a counter goes through a repeated sequence on n counts, it is known as a modulo n counter, or in short they are known as mod n counter. If you have a 4-bit counter, it actually goes through a repeated sequence of 16 states, hence it is known as mod 16 counter. The BCD counter is mod 10 counter since it goes only through 10 states. Now, you have come across with different types of synchronous counters and you will be clear with the difference between the synchronous and the asynchronous counters. Counters come handy wherever the counting is involved in the digital systems. With this, we are winding up the session. We started with up-down counters, then we moved on to BCD counter, ring counter, followed by modern counter. Each counter has its own unique features. The change of state of each flip-flop at the occurrence of a clock pulse was explained in detail for each of the counter. Hope you are clear with each and every concept. Now, you are able to design digital circuits for any number patterns. Try out and come up with innovative designs. Thank you for watching. See you in the next session. Bye.